Change that much. So any problems on the edge, just want to be. Yeah.
All right. So we're live. Things of relevance. There was a practice assignment before class today. I hope everybody did it. We have some homework due tomorrow. We're kind of continuing on with our Bodie plot. And then we'll have some homework due on Friday. And then thing to look forward to, of course, is we have an exam next Tuesday. Kind of nickel. Anybody want to make that? So always good time. I should point out that I know this has come up before, but I give you all the historic crib sheets on the exam number 1 crib sheet or the amplifier circuit. Just to remind you that they do exist on the crib sheets. They're there for your reference. Other than that, our lab is due tomorrow. Don't forget lab. What were we on? 4? 4 is due tomorrow, and then lab 5 will due tomorrow, and that will be due next Tuesday. So, other than that, I think that's about it for administrative stuff. Yeah.
I didn't get really creative for 17 created, and I got point taken on, points we talked about a lot, well, labeling my plot with the title. Oh yeah, I got to agree with that. I labeled that. I don't know.
Yeah, it's not something I would have pushed necessarily.
We have to have labeled access.
You should definitely label that. Otherwise, it's not full information.
I guess, but
I mean, a plot title,
probably.
I wouldn't have taken off a point for that.
Yeah. Okay.
Sure, submit a regrade. Steve Bronson said plot to the need to dial. That's fun. So, anybody else, any administrative questions? Everybody's good? All right, so 3 people will be questions. This fellow's not here. Who wants to go first? Mr. Nazari, you're here. Did you prepare? No question waiting for you. Mr. Evan. Yeah.
When we get to the divvy part, how's that gonna go? That's, looks like that's coming up.
That'll be our stepping stone into unit 4. So there's a crossover with the transfer function that steps into differential equations. Which hopefully, at this point, you have started to solve initial value problems in your DFQ class. I sincerely hope so. You're on the spot.
Asking a question. But why do we not care about like overdamped and critically damped as much as we do fiber?
So that's a good question. So if I'm designing a filter, let's say a low pass filter for argument's sake. And we'll just make this 0 dB, make that our pass band. And if I have an overdamped case, I have 2 real poles, right? I think it does something like that. There we go. So familiar? Everybody okay with that? We have a pole. I could make up some numbers. Call this 10 to the 2 or 2. Call that 10 to the 4. That's minus 20 dB per decade. Minus 40 dB per decade. What's the only frequency that matters in terms of this low pass filter characteristic? Only one frequency matters to them. What's the frequency that matters to them? The cutoff frequency, right? It's the only thing we care about. So Our cutoff frequency is here if I add my corrections. Things we've talked about. Remember, these are both poles. So we're at -3 there, and we're at -43 there. But the -3 dB point gives us our passband. I should point out, this is an overdamped case, 2 real poles. Why do I not care? Good question. Why do I not care? What are our goals with regard to a low pass filter?
Have it work.
Have it work, but
Steep slope.
steep slope, steep stop band slope. So we transition from the pass band to the stop band. What's our slope? -20 dB. Exact same thing we can do with a first order circuit. Sure, once we get up to 10 to the 4th radians per second, we transition to -40 dB per decade. But that doesn't matter. We don't care about that. What we care about really is how does the slope behave right away? And we're interested in that. Yeah, at higher frequencies, great. We attenuate, but we're already attenuating. We're already, just a general reminder, I haven't labeled the y-axis, so maybe -1 point for me. But this is -40 dB right here. -40 dB is 2 orders of magnitude down. So something that's in my pass band, if we have 5 volts here, we get 5 volts out, or pretty close to 5 volts. If I put in 5 volts here, and we're at this frequency, we have 0.05 out. Yeah, all right, we can go steeper than that, but we haven't gained anything. There's nothing really particularly good about this overdamped low pass filter response. Does that make sense? I mean, it's kind of an important conceptual discussion. Yeah.
Unless it's a band pass filter, 5%.
Well, the only way to get a steeper slope is to have a higher order circuit. So here's an overdamped case. We can look at the critically damped case. We can do the same thing. Here's 0 dB. And maybe we're at 10 to the 3. And we'll call that -40, -80, 10 to the 3. So again, low pass filter, this is critically damped. What's my correction at my cutoff frequency? Or it's not my cutoff frequency, I should be careful. What's my correction at the pole? Not -3.
Oh, does that get corrected?
What type of pole is it? A transition from 0 dB to -40. What type of pole is it? It's a double pole. What's my correction? -6. How do we define the cutoff frequency? Somewhere over here, we have -3 dB. So if I told you design a filter that has a cutoff frequency of 10 to the 3, you have not met spec, which is part of what we're going to practice today. But why is this filter arguably, at least maybe, considered better than this one? I mean, what's the improvement aside from the changing of the cutoff? But what's the improvement here? Steeper slope. I transition to a steeper slope. On my pass band, I transition to -40 dB per decade. I have a steeper slope. It's a better filter, but I have not hit my cutoff frequency where I want it to be. I want my cutoff frequency to be 10 to the 3. How do we solve the problem? Well, ouch. We can fudge it a little bit and say, all right, I can just design a critically damp filter. And rather than make the pole at 10 to the 3, I'm gonna make it at 2,000. You know, a little bit higher, and then that way my cutoff frequency maybe is 1,000, a little bit less. Does that make sense to everyone?
Like a frequency 1000.
I can just move my pole over to the right, higher frequency. But if I move my pole over to the right, then my 3 dB point is moving to a higher frequency as well. I mean, I can crunch some numbers and figure out what that is, but there's a better way of doing it. I can underdamp the circuit, which was our last video. And if I underdamp the circuit, then I can say 10 to the 3. And again, here's my straight line approximation. So 0 dB minus 40 dB per decade. So minus 40, minus 80. And I can make that minus 3 dB. But we already know if I'm critically damped, the correction is minus 6 dB. The only way to lift this up, to have a correction that's higher than minus 6, is to underdamp. And technically, the more strongly underdamped I lift this up, and then as we saw in the lab last week, I can be somewhere way up here. If it's what I would call strongly underdamped. Not a good circuit design. It is something that exists, those type of circuits exist, but not a good filter design to have this like bump thing going on. It's not the goal per se. I mean, this is kind of our motivation for doing this. So yes, I give you the overdamped case to do, blah, blah, blah. You know, it's a class exercise, practice understanding transfer functions and Bodie plots and stuff like that. But we don't care. What we really do is work with underdamped circuits to get sharper corners, so to speak. I mean, it's not a true corner, but to get 3 dB points where we want. And we can, and we'll do this in class a little bit today, we can make this steeper and steeper within certain limitations.
Thank you.
Does that make sense? I mean, this is kind of for everyone. Does that make sense? This is our motivation. So it's not just, you know, yeah, I need to get through circuits so that I can take the next class and graduate. Forget if I ever learned anything about this, which is okay. You don't have to memorize filters. You know, and lots of electrical engineering jobs that don't have anything. With that said, it is kind of nice to know why are we doing something. So early in the semester, we analyzed a lot of stupid circuits with node analysis and mesh analysis. Served no point at all. This actually is verging on the practical. I mean, you look at analog filter design, and this is the type of thing we do, underdamping circuits. I will admit analog filter design is, again, something that's not as common as it used to be. If you go find old stereo equipment, it was all analog circuits. Nowadays, in your phone, it's all software, at least for your acoustic stuff. Digital circuits and D to A converters, digital to analog, and then ultimately a little bit of analog circuit, but a lot done with software. But this gives a motivation for how to understand that software when you take a class like Signals next semester. All right. Any other questions? These are good questions. It's important to understand why we care about this. Yeah.
More about like the lesson, it's just I guess like finding the correction,
Yeah.
like maybe like do some practice.
We will for the underdamped case.
Yeah.
I mean, to qualify that, for the overdamped and the critically damped case, you've already done the practice. When we have real poles, when we have zeros, we know what the corrections are. 3 times n, where n is single, double, triple, whatever, minus, 6 for a double full, plus 3 for a single zero. There's nothing new about the critically damped and overdamped case in terms of things that we've done. But the underdamped is our strong finish, so to speak. And our journey to get there today, we're just going to revisit some of the discussions that we had a little bit earlier. So we have our RLC circuit. I want to point this out. Things we discussed before. I'm going to do this quickly. We've already done this analysis, so I'm going to skip a bunch of steps that we've done before. Here, the L, so across our inductor, L for inductor in this case. If our output is across the inductor, then we know our transfer function. I'm skipping the voltage divider stuff and just dumping straight into our transfer function, is ZL over ZL plus ZR plus ZC. Everybody agree with that? It's a series RLC circuit. Voltage divider concepts apply, 3 components in series, no problem with voltage divider. The component we're interested in the numerator over the sum of the 3 of them in the denominator. We can plug in our impedances, SL plus R plus 1 over SC. Hopefully we're pretty comfortable and kind of remember those. And then we can do the cleanup process. I'm not going to write out the mathematics. Ultimately, we get H of S equals S squared over S squared plus R over LS plus 1 over LC. There's our transfer function. We've seen that a couple times before. I think I made you go through this process sometime last week, which is why I did it a lot more quickly than we have in the past. That said, I want to emphasize what type of filter is this. So in the limit, as omega goes to 0, H of S is approximately, well, what do we keep in the numerator? Stays the same. There's nothing to compare it to. We keep the S squared term. There's no S plus anything. So we get S squared over, what's the dominant term in the denominator?
SC.
1 over LC. So good answer. S is going to 0, or omega is going to 0, technically. So our S squared term is going to 0. Our R over L times S term is also going to 0. 1 over LC is constant. And as was answered, 1 over LC. So we get 1 over LC, which is some number. And in this case, as omega goes to 0, then how does this transfer function behave? It's heading to 0. It's going to 0. There's our approximate transfer function. We want to keep that. Remember, we're never saying omega is 0. We're just saying it's becoming small. But our transfer function in terms of magnitude going to 0. And then in the limit as omega goes to infinity, well, once again, our numerator, S squared, what's the dominant term in our denominator now? S squared. So S, or omega, is going to infinity squared. Here, omega is going to infinity, but it's just going to infinity to the power 1. So this is going to infinity faster. And 1 over LC is still constant. So we wind up with our S squared. And so at high frequencies, our transfer function is 1. What type of filter is this? Low frequencies, output is 0. High goes to 0. High frequencies output goes to the input. Just to emphasize again, I know we've said this before, and I think everybody's comfortable with it. When the transfer function is 1, that means the amplitude of the output is equal to the amplitude of the input. If that doesn't seem familiar, make sure you write that down. So here's our low pass filter. And likewise, we could say, all right, if V out is across our capacitor. So plus minus. And we can do all the same discussion. H of S is ZC over ZC plus ZR plus ZL. Do the substitutions, 1 over SC, 1 over SC, plus R, plus SL. Clean it up, and we get 1 over LC over S squared plus R over LS plus 1 over LC. And again, we could have that same discussion. And the limit as omega goes to 0. Our transfer function is approximately what? Well, again, in the numerator, nothing to compare it to, so we keep that term. We always keep the term if it's by itself, if there's no parentheses around it, or we're adding it to something else. What's the dominant term in the denominator again? Same answer. It's 1 over LC. So S squared going to 0, R over L times S going to 0. No surprises there. And we get 1. And likewise, limit as omega goes to infinity, H of S is approximately 1 over LC again. And hopefully we all agree S squared is our dominant term in the denominator. And what happens is omega goes to infinity. Well, we have something over omega squared effectively. And so we're going to 0. Exactly. And now what type of filter do we have? Hopefully we all agree. Low pass filter. That said, I want you to derive the transfer function for the output across the resistor. So there's your job. You can write it down quickly because I forgot to set up grade scope for the in-class assignment today, so I'll do that while you're doing this derivation. But your goal, what's the transfer function for the output across the resistor? Check your neighbor's work. While I quickly pop up grade scope.
So Daily, you gotta call. Yeah. Someone just.
Oh, I'm doing everything.
Sitting back calling.
So check out. Yeah.
There you go.
So,
You're right. Zero. Hey, Mr. Zero. Good assumption.
Oh, yeah, I got that.
Yeah, yeah. You know me, Victor, I'm just like really, really cautious guy. Yeah, I haven't answered a call from Victor.
From Victor?
Yeah, apparently he gets called.
I keep getting calls, so it's like, hey, is this Victor? I'm like, no, this is never really gonna call.
Yeah, he just did it.
I gotta determine.
The transfer function sister to be hard by L times. So that's
Yeah.
right.
Yeah, that was gonna be the way you wrote it, but yeah, yep, straight.
You see the comments he had shot by him. The guy that says like, up to whatever it is.
What's your?
I don't like that one, it's soda. Yeah, I don't know, but yeah, what's, that's our.
Oh, that's right. Yep. No one wants a nickel? A nice shiny nickel? Not very good at talking.
It's actually not a joke, I do.
Yeah, my awareness is gotten old.
I got, more over on that.
That's the right tool. All right.
And then you must.
No, no.
Right, so this is something that measures the divide. And I don't know if you want us to be able to have them fast, right?
Yeah, no, well, I think it should just simplify as much as possible, and then whatever you simplify.
Oh, okay, those.
Yeah.
Now, you have all the rest of it.
Yeah.
This is the best I see.
Yes. Yeah,
I don't know.
So,
We have zero everywhere. Or do we?
Mega group, zero. Then you say, I'm gonna see big one over. Oh, yeah. Or, which means you're right. Still, it's zero.
Yeah. Okay.
Each of this.
So we add some to that square. Okay.
Alright, this goes to.
So that's the difference.
This is the first one.
And if it was 0 over 1 over.
Oh.
Do we have to do that?
So it just
Zero.
That's
the limit, that's the part. Higher, and like this is, that's blood, right? And so, and the other is getting blocked. That's dominant. That's quite the limit. Wait, so it says it's not even dissolved, like, it's dominant.
You multiply and S. These are multi.
There's no comparison.
There's nothing you multiply by.
It's R over L. Because there's no, there's nothing to compare it to. What's the dominant term? Denominator. So when the beta is going to zero, which one goes to the biggest?
Zero.
Whatever else. It's our.
It's just like. Yeah.
Does that make sense?
What? It was tiny. Set of years.
Complex roots, right?
And I
What's that?
Yes.
Not complex roots. Well, we don't know what type of roots they are until we know values for R, L, and C. So we can't make any statement about the poles until we know what the numbers are. Everyone agree?
Yeah.
What's the limit as omega goes to zero?
Zero.
Zero. What's the limit as omega goes to infinity? Not one.
Also zero.
Also zero. So our limitations, if we write it out, we get dominant term R over L times S over 1 over LC. Yeah, it looks a little messy, but that's going to zero. You can do some canceling and whatever, but we have S in the numerator and omega is going to zero. And so if omega is going to zero, our transfer function is going to zero. Likewise, we have R over LS. It's still our dominant term because there's nothing to compare it to over S squared, which winds up being R over LS, which is also going to zero because we have S in the denominator and S corresponding to J omega, omega going to zero. We have 1 over infinity, or sorry, omega going to infinity, 1 over infinity, 0. So we have 0 on both sides. What type of filter is it? Bandpass. Why? Well, because we think it's a filter and it's certainly not low pass and it's not high pass. So good process of elimination answer. Let's check. There's a way of check. A way to check. So we wrote out H of S equals R over L S squared plus R over L S plus 1 over LC. Let's recall something that we've seen. R over L is 2 alpha and 1 over LC is omega naught squared. Right? That said, let's see how the transfer function behaves when omega equals omega naught squared. Equals omega naught. When omega equals omega naught, we can do that substitution. H of J omega naught is R over L, J omega naught squared plus R over L, J omega naught plus 1 over LC. But we know what omega naught is. We can plug in 1 over square root of LC. Do that substitution. Gets a little bit messy, I suppose. J R over L times 1 over square root of LC. J 1 over square root of LC squared plus J R over L 1 over square root of LC plus 1 over LC. A little messy looking, but do the substitution, plug in the expectation. If omega is our resonant frequency, you get this equation. What's J squared? -1. What's 1 over square root of LC squared?
Just one, very LC.
1 over LC. Negative 1 over LC. Positive 1 over LC. What happens to the first and third term in the denominator? They're equal and opposite, we could say. They cancel. Those two cancel. Cancel, cancel. What do we notice about this term and this term? Equals 1. At the resonant frequency, our transfer function is 1. At high frequencies, transfer function is 0. Low frequencies, transfer function is 0. What do we have? We do have that bandpass filter that we expected it to be by process of elimination. Yeah. Do the same, what do you mean?
Like how we do as there's infinity and like what's the zero? You know,
Not quite following.
R over LS over S squared, R over LS over.
Well, we have to cancel these two first before, yeah, so ultimately you're right. This over this, but that's only true when these are summing to 0. Is that what you're saying? But we had to make that argument first that this is the negative of this, which only happens at the resonant frequency. So at the resonant frequency for this bandpass filter, the dB value is 1. The output equals the input. And on either side of that, it's probably pretty close, but. Final question then is, what happens if we measure across L and C? So if we do something like this, plus minus, there's my V out. H of S in this case, ZL plus ZC over ZL plus ZC plus ZR. Everyone agree? We're okay with that? I can add those two together as an equivalent impedance. Numerator. I can go through all the math. And I get S squared plus 1 over LC, skipping a bunch of the steps, plus R over LS plus 1 over LC. Well, once again, 1 over LC is our resonant frequency. If I go through that same process and say, what's the frequency or what's the transfer function at omega naught at the resonant frequency? What happens to my denominator? You just had that discussion. At omega naught, my numerator goes to 0. So at omega naught, this goes to 0. Likewise, as omega goes to 0, what happens? Turns out H of j omega, I can write it as H of S if I want, goes to 1. As omega goes to infinity, H of j omega again goes to 1. You can think it through, you should be able to see it a little bit quickly by now. What type of filter is this? Still a filter. We haven't talked about it a lot. Yeah. Band stop filter. Band stop filter. So it's our fourth filter that we don't spend as much time with, but here is how we define our band stop filter. I should point out one of the reasons that I went through all this is the type of filter is dependent on where you define the output. That's one of the morals of our story here. So transfer function, denominator exactly the same for every situation. I mean, we don't know what the damping is because we need numbers. But transfer function, denominator the same, numerator is different. And numerator is defined by where we measure the output. Output across the capacitor, low pass filter. Output across the inductor, high pass filter. Output across the resistor, band pass filter. And then here, output across both the inductor and the capacitor, band stop filter.
What about resistor and capacitor?
I don't remember. It's something weird, not important. I think I've done it once or twice. Then it devolves into a silly math problem. I mean, so math exercise. As opposed to the four that we've looked at here, arguably practical. So I don't, again, I've never myself applied a band stop filter. I have done low pass, high pass, band pass.
If we can make a bandpass with the second order, why do we wanna put a op amp in between the bandpass?
So. I mean, that's a good question. If we can make a second order band if we can make a band pass filter with second order circuits, why would we do it with first order circuits, to reword your question?
Yeah.
Because first order circuits, we need that op amp. I mean, arguably, we would, less components. The only kind of restriction there is inductors can be problematic. So it depends what type of components we're working with. So there are, if we're working with reasonably higher power, we may want to avoid using inductors in our filter circuits. By high power, I mean like, stadium level amplifier circuits. If you're going to a rock concert or something like that. I don't know. I don't even know who I'd ask. I am curious now. And I don't know how much of that has been replaced with software as well. I know the dB levels are high. There's a fair bit of power that goes into a concert. So, revisiting our discussion of low pass filters, or of types of filters, I should say. And then picking up, we already started our discussion today on motivating why we're looking at underdamped circuits. And here's just, if we're given an underdamped circuit, here's our process. You did this in the preparatory assignment. We have a correction. So the correction for the underdamped circuit is a special correction. To emphasize that point. So it should be in your notes. For our underdamped circuit, here's our special correction. It is still relative to the straight line approximation. So it's, plus whatever, minus whatever, relative to the straight line approximation. Yeah.
Down for the.
What's that?
And that correction is for the.
Only for the underneath. So. It does have other settings where we can use this information, but this correction is for the underneath. So, and again, it gives us the actual value of resonant frequency. So when we're talking about underdamped, I just copied this from our prep assignment. We care about the resonant frequency. We don't care about the poles anymore. Poles are complex. Complex poles, 1000 plus 500J, that doesn't mean anything to us. You cannot dial that into the function generator. See, no setting for imaginary pole settings, imaginary frequencies on the function generator. So we start to talk about the resonant frequency. That's the important concept. And arguably, I'd like to move past this a little bit and start looking at filter design, but I can pause here for a moment. Does anybody have any questions on this process? Yeah.
You said -6 dB as a correction.
Minus 6 dB, because why? How many poles at the frequency? So remember, our critically damped case is if I went and said, this may be the example I used in the prep assignment. I tend to use things that are easy on numbers. Easy numbers to use. If we go through that, alpha is 1/2 R over L. We crunch that out. That's 1,000. Omega naught is square root 1 over 0.1 times 10 to the minus 5. That's also 1,000. Alpha equals omega naught. So here's our critically damped. I sped through that, but I think we've seen that a bit before, so we should be comfortable. That said, what does that mean? Our transfer function, I could go through the process. We could look at the output across the capacitor. H of S, in this case, 1 over LC over S squared plus R over LS plus 1 over LC. We can crunch through all the numbers. We get 10 to the 6 over S squared plus 2000 S plus 10 to the 6. And it turns out this is S plus 10 to the 3 squared. For the critically damped case, the resonant frequency, which equals our attenuation constant, is our pole, and it's a double pole. Now, I sped through that, but I think we've seen it before. Is everybody okay with that? Are there questions on what I did pretty quickly there? With that said, so to answer your question, I have a double pole in the critically damped case by definition. What's my correction for a double pole? -6. So -3 times n, where n is the number of poles we have at that frequency. So we have a double pole, and it's 2 times -6, or 2 times -3 is -6. Does that answer your question? Yeah. I was just scratching your head. Yeah.
So where do you transfer from?
Then what's my correction? If I have a triple pole, -9. Right. And you just keep going, quadruple pole, -12. What does that do for our cutoff frequency? It keeps shifting our cutoff frequency further and further from where we want, which is our goal. So, anybody else have any questions, or are we good? Yeah. No, we get critically damped is independent of the type of filter. So, what critically damped only depends on what? Or underdamped or overdamped. What does it depend on? The denominator. It's the numerator that tells us the type of filter. So, I mean, that's arguably worth writing down. I mean, numerator, which is from our output, wherever that is, type of filter. Denominator, type of damping, completely separate. Completely independent of each other. So I can build the circuit and not tell you where the output is, and we know whether it's overdamped, critically damped, or underdamped. So once I pick an output, then I know what type of filter I'm working with. And let's start with this one. What's my cutoff frequency?
-3.
What's my frequency? So it's at the -3 dB point. What's my cutoff frequency? Then the problem. Omega C is 10 to the 4. So omega C is 10 to the 4. What does my filter look like? Here's my straight line approximation. There's 10 to the 4, minus 80 dB per decade. And then my passband, in this case, 0 dB. Stretching, or you have a question? Good. How do I go from 0 dB to minus 80 dB? Important concept. How do we change the slope suddenly by 80 dB? Quadruple pole. We have to have a quadruple pole. I mean, we can, it's not really pole per se. But we can kind of pretend quadruple pole. I don't remember how to spell quadruple. Is that right?
What creates like double
Okay.
and quadruple poles? What is causing that?
I mean, it's the circuit we design.
Okay.
So how am I going to get, per your question, a quadruple pole? Or more specifically, how am I going to get something that has minus 3 dB at our effective pole? I mean, what's the correction for a quadruple pole?
16.
Not 16.
No, minus 12.
Minus 12. You're off by. Remember, it's minus 3 for 4 times minus 3. Minus 12 dB, or minus 12 dB. What's the only thing that can lift that up?
0.
It's the only type of circuit. What's the only damping that can bring that up? It has to be underdamped. Our circuits must be underdamped because if we have real poles, our correction is minus 12. In order to lift that up, we have to have an underdamped circuit.
And that's why underdamps are so much more important than the other two.
Yes. So we must have an underdamped circuit. Must have underdamped circuits. We should do plural. Why am I saying circuits? If I have one underdamped circuit, what's the slope going to be in my stop band? Not 20. Second order circuit.
Oh, it's 40.
Minus 40 dB per decade. If I underdamp second order circuit, underdamped, low pass filter, I go from 0 dB to minus 40 dB because I'm crossing effectively a double pole at the resonant frequency. Remember, when we're talking about underdamped, we have complex conjugate pair poles. Something plus J something, something minus J something. There's a pair of poles. It's a double pole. But we're not talking about the complex numbers, we're talking about the resonant frequency instead. And we can pretend our resonant frequency is a double pole. So double pole is going to give us minus 40. What do I have to do to get minus 80? Well, second order circuit's going to give us minus 1. Second order circuit's going to give us minus 40. What do I have to do to get minus 80?
Add another circuit.
Second order circuit. Where's my output for both second order circuits? What type of filter am I building?
Low pass.
Where's my output? Capacitor. Output or a low pass filter across our capacitor. So I could get partial credit on the test by saying, here's my input, resistor, inductor, capacitor, resistor, inductor, capacitor. What do I want in between there? Oops. An op amp. I need that isolation. R, L, C, R. There is my V out final, but there's my V out for stage 1. What type of op amp circuit is that again? The voltage follower with the transfer function equal to 1. It's our isolation op amp circuit. Yeah.
So having an op amp is what makes it the difference between a first order and a second
No.
order circuit.
Having an op amp is what makes us be able to do this as a multi-stage circuit, H1 of S times H2 of S times H3 of S.
Yeah.
If I got rid of the op amp, what can I say about the capacitor? It's now in parallel with this stuff. It's a much more complicated transfer function.
Can you go back to the other slide?
Does everybody agree with our discussion so far?
You could go back.
Again, this is your time to ask questions. So, what do I know? Yeah. What's that? So what is the second order RLC circuit? What slope do we get in our stop in? Minus 40. Why do a second one? Because the slopes, when we multiply in dB scale, slopes are additive. Likewise, leading to our next discussion, the correction is additive. What does our overall correction have to be at this quadruple pole, 10 to the 4? What defines the cutoff frequency? -3. So what's our straight line approximation? Here's our straight line approximation. We want our actual value to be -3 dB there. There's our actual value because that defines our cutoff frequency. What do we know? I want to find values for RL and C. What do we know? This is omega naught because we're under damping. That cutoff frequency is omega naught. What else do we know? Here is our follow-up. So we have one equation. We want to find values for RL and C. We've been assigned to design this circuit. We have our output. We know we have a low-pass filter because we're measuring across the capacitor. We know we're going to get to 80 dB per decade because we have 2 second-order circuits that have slopes of -40 dB per decade in our stop in. We know our cutoff frequency is 10 to the 4, which is at our resonant frequency, which is 1 over square root of LC for this circuit. So we have 3 components defined. Arguably, we could say we have 6 components defined, but we could make both of these stages exactly the same and make our life a little bit easier. We don't have to do that. Yeah.
Is there like a realistic limit for like stacked poles? Like you won't go above eight, what's it called, double, quadruple?
I mean,
To be.
I don't know. So I've never worked that high. I know that you can design very steep roll off with multiple poles and zeros. So
But then it's like you said, an ideal, I don't know the term for it, but like pass band, stop band, or ideal like pass band has the steepest slope. So if that's what makes the slope steeper, why not just stack like 100 on?
oh well, you're limited in size and
Like realistically, like needing it.
well, so all right, let's follow through on a second for a second. My overall correction at my resonant frequency is -3 dB. The corrections add per stage. So what do I want to do? Stage 1, pick a correction.
+6, -6,
So then what does stage 2 have to be?
-6.
Now the overall correction has to be equal to what? -3. So per stage, corrections add a pole or 0. Add a pole. And this isn't important, but I'll include it. Or 0. The corrections from each stage will add. at the cutoff frequency, we want a correction of -3 dB. Relative to the straight line approximation. If we have two stages, two-stage circuit, stage one, stage two. What do I want my correction to be for stage one? You pick. Pick a number.
Minus,
All right. What does my stage two correction have to be then?
oh, because it has to equal -3 on that side.
This is perfectly fine. 0 dB. What's another possibility?
-6.
All right. What does this have to be?
+3.
I was looking for a possibility that would save me workload. What's another possibility?
-18.
That's not going to save me work.
So,
It's not going to save me work.
see,
Which points? So what can I say about the RLC values in this circuit relative to this circuit? They're going to be different.
yeah.
They have a different correction. Component values have to be different. I mean, some of them can be the same, but
But see, wouldn't it be harder to get -1.5 and then get -3 and 0?
would it? Why?
I just built the same circuit.
What's the advantage with this? Exactly the same RLC circuit. This is not a bad choice. This first row, not necessarily bad. Second row, not a great choice, but that's was a good one to bring up. First one actually gets implemented, I think. So, I don't know if there's any advantage relative to this. I'd have to go look at the Wikipedia page for Butterworth circuits. But yes, -3 dB. So if we make that choice, stage one, -3 dB correction. Stage two, 0 dB correction. We get two different circuits. And how does that play out for us? Where's our correction come from? It's -3 dB equals 1 over 20 log of 1 over 2 times the damping ratio. 0 dB, put that little 1 there because that's for circuit 1. 20 log, 1 over 2 times the damping ratio for circuit 2. Do we agree?
Yes.
For underdamped circuits, this 20 log, 1 over 2 times the damping ratio, that's our equation for the correction. I should do a little aside. I did this in the video, but if I have some dB value, 20 log of some constant, I'll call it A, then 10 to the D, let's write this a little differently. A equals 10 to the dB value over 20. I think I touched on that at some point in the video, but that's an equation worth being familiar with. It's just the opposite side. How do we solve for A? if we know the dB value. There's our formula for solving for A. So I could go through my process here and say this gives us 2 times the damping ratio. Well, ultimately, if I do all the math out, I get a damping ratio of 0.707. Here, I get a damping ratio of 1. Sorry, 1/2. Zero point. And by definition, kind of stepping through, our damping ratio is alpha 1 over omega naught, alpha 2 over omega naught. We know what omega naught is for both circuits. I suppose I could throw that out there. Why do we know what omega naught is for both circuits? Because it's going to be the cutoff reads. It's going to be the cutoff reads. So there's our relationship. We know what that is. I can go through a little bit more math. Alpha 1, 0.707 times omega naught, 10 to the 4th, and we get 7070. Alpha 2, 0.5 times 10 to the 4th, we get 5,000. This is 1/2 R1 over L1 equals 1/2 R2 over L2. Alpha, 2 alpha equals R over L, or alpha is 1/2 R over L. Do we agree? That's it. That is the only information we have. We have 2 equations and 3 unknowns. We're designing, what can we do? 2 equations, 3 unknowns, what are we trying to find? We're trying to find R, L, and C. What can we do? Well, ultimately we have to plug in numbers, but we have only 2 equations. So what do? You're the designer.
Trying to find R, L, and C.
Trying to find R, L, and C. We have 2 equations now. We have,
Oh, just
this is circuit 1. Call this circuit 1. This is circuit 2. And then for both circuits, we know omega naught, 10 to the 4, is 1 over square root of LC. Or if you like, 1 over LC is 10 to the 8. That's it. Circuit 1, circuit 2, we have an equation for R and L. Both circuits, we have an equation for L and C. That's it. That's all the information we can pull from our specs. What do? Yeah, you don't give up, and it's not a system of equations because it's not complete. Yeah. Pick a value, and I would qualitatively say not random, pick a good value. I mean, if we're actually designing this, pick a good value. On the test, I let people get away. I've seen people put, and don't do this, but put like 0.1 ohm resistors as their filter design. I give full credit because mathematically it's correct. I mean, I assume we have to pay something. I've seen it more than once. Or 1 ohm or 2 ohm or stuff like that. And I don't want, I mean, if that's what you wind up with, just leave it. Don't try to make it better. But if we have a fraction of an ohm in our circuit design, what's the problem? What is the problem?
You're not gonna get it. You're not gonna be able to find a fraction.
We already have a fraction of an ohm in the wires. So we're not going to be able to do it. We want reasonable value. I mean, I've seen students give me 10 farad capacitor values in circuit design. Historically, a 10 farad capacitor was like as big as this room. It's not true. You make them small, but not a practical design, really. So, yeah.
I would say if everything's the same relationship, could just be multiplied from
Well, you gotta be careful. This one's a square root relationship and there's inversing. So, no, you can't. If you multiply everything by 100, you've changed your resonant frequency. So, need to pick a value. R, L, or C, and use the above equations to find our other component values. We're gonna practice this in the lab tomorrow. So we have a good opportunity to look at some of this. It's a big deal on the ending up. I'm gonna give you in the last few minutes. I want you to just set up the circuit. You don't have to find the exact values, but I want you to reason through. Build a high pass filter. With a cutoff frequency of 10 to the 3 radians per second. And a stop band of 60 dB per decade.
This part of the.
Yeah. You don't have to find values, but I want you to get a schematic down, regional schematic, label where the output's gonna be. Yeah.
Stop it at 60. Does that mean like it stops?
The slope is 60 dB per decade.
Oh, okay, okay, gotcha.
These are all only voltage based filters.
We can do it with current.
But the op amp will have,
You can do a current amplifier as well. There are current amplifiers.
so the voltage is zero, current is.
Current in, current out. It just depends what you're measuring.
But I thought like the input for op amps could be voltage wise, you know. But you know, current.
But if you have current, you have voltage too. They go hand in hand. Just depends on what you're measuring.
But then wouldn't it mess like, we will have like in parallel, so.
The op-amp circuit is the same. It's just again how you define input and output.
My question is, do we want it at 3 decibels all the way? Cool.
Cutoff frequency is by definition minus 3 dB.
Oh, okay.
So cutoff frequency says minus 3 dB.
Okay.
You need 2 circuits. That is correct. What's that? Correction is minus 3. For cutoff frequency, we're always talking about the total correction
We can do the slope.
being minus 3.
We can make the 60.
Talk to your neighbors.
How,
Want to talk out.
Right.
what sides?
Well, I told you what the cutoff rate.
No, I know, but like, 60 dB per decade, we can make the circuit. That
Correct.
Like the circuit.
Yeah, that's not, and I already got that.
They go hand in hand.
Wait, is it the value?
Yes.
Okay.
Could be. Pass in there and.
Oh, no, resistor.
Or you'll. Take the voltage and. Back.
Now I will.
So some. Right. But you like that.
Right. So you have second order and second order.
Yeah.
With my slope and.
This is
That was the tricky part.
this is how I would set it up. If this is what I want as my
Well, not quite. So think about the type of circuit. Think about the circuit that you have to lay out first. What's gonna give you 60 dB stop in?
Second.
First,
Everybody hear that? What's gonna give you 60 dB? If you use 2 second orders, what do you have? And do 2 second orders. If you do 1 second order, what do you have? 40. How do you get 60? Second and a
it's a resistor.
first order circuit. What's the cutoff frequency for a first order circuit? What's the pole? What can we say about the pole for a first order circuit? Single pole, and it is not complex. It is real. What's the correction for a first order circuit? Always. Always. First order circuit correction, single pole, -3. We are stuck with -3 correction on our first order circuit. Which means the second order circuit has to be what? 0 correction. Should draw out the circuit. What circuit would you draw out? You don't have to crunch the numbers, but do as much as you can and then upload. Don't forget upload. Yeah.
Does it matter? Order of the first.
Yeah, that's a good question. So the order doesn't matter. It's asked. Should we do the first order before the second order before the first order? It does not matter because they multiply. We're looking at multi-stage circuit. H1 times H2 times H3 is the same thing as H3 times H2 times H1.
Yeah.
Doesn't matter how we multiply. If anybody needs more bony plot paper for their homework and stuff, I brought some in again.
Use supply.
Year supply. Don't forget upload.
You know what's crazy? This is we have, including this week, we have more and more loose classes. If you look at it, that's
Is there any more
loose classes. Okay, you'll have to study. Also, check for any much where you're gonna pass the. You're gonna not get the last.
You always have that has capacitor in it.
Like, he's oh boy.
No, that's a lot.
I don't know. What? Totally.
That is actually.
That's what makes. Is the class-